Okay, great. Okay, so thank you, everyone, for coming today. This is the first seminars that we're having as part of this series. It's been a long time since we've had these things in person, so I really appreciate everyone coming here. And thanks everyone to the online participants. So today we're going to be having Yue Dong. So she's a NOAA postdoctoral fellow who's sitting technically at Lamont.
Yeah.
I think she spends most of her time in the applied math department at Columbia, but probably many of you have seen her because I think she's working on several projects with many of us. Yui's been doing very interesting work, looking at climate sensitivity, TCR, basically things that are really interesting, I think, to the GISS group. So with that, the only other thing I'm going to say is that we're going to do as we've done in the past, where if people have questions, obviously, if you're here, just raise your hand and we can ask them throughout. But if you're an online participant, please just indicate the question in the chat, and then I'll ask that. And so, fingers crossed, everything technically goes smoothly. So with that, please, Wyatt.
Yeah, thanks for inviting me and also for introducing me. I'm very excited to be here speaking to you in person while you are enjoying your pizza. Yeah, and also very excited to come to the building, very mysterious building nearby Columbia. So I'm currently a postdoc at Lamont. And Columbia, like APAM, I sit in APAM most times. And before coming to New York, I did my PhD at the University of Washington in Seattle. So I moved from West Coast to East Coast across the whole country in the beginning of February. So it's been over half a year, I guess. Yeah, pretty enjoyable experience in New York. I'm very impressed by the vibe of the city and also climate here. Anyway, yeah, today I'll be focusing on the so-called sea surface temperature pattern effect. Some of them from my PhD thesis, and some of them are from my recent work thinking about the potential role of Antarctic ice sheet meltwater and its implication for pattern effect, which I hope can be of interest to the GISS colleagues. Yeah. Okay. I believe I don't have to explain this, right? ECS equilibrium climate sensitivity to you guys. Equilibrium, a long-term global means of a temperature response to a CO2 doubling relative to pre-industrial levels. Well, there are multiple lines of evidence to constrain ECS based on like the recent WCRP reports, the Sherwood et al. 2020 paper, including paleoclimate record, including process level understanding. But here I want to show two most common ways to estimate ECS from model simulations. So one is so-called abrupt full-time CO2 simulations, one of the DEC experiments. So fully coupled models, you abruptly quadruple or double CO2 and have a constant for 150 years as a standard time period required by CMIP. But usually at the end of 150 years, the whole system is not fully equilibrated. Thus, you can practically use the so-called Gregory method, the Gregory regression, regressing to a radiation imbalance on the vertical against the temperature change. So you can extrapolate long-term warming from this point as an ECS for CMIP models. Kind of idealized, you assume linear regression, but this is still the most common way to estimate ECS for models. So this is one way. Another one is to use, sorry. Not sure what I, does it bother everybody? Could I move it? Oh, sorry.
Yeah, I can probably just amend this.
Oh, yeah. Okay, another one is to use historical energy budget constraint. So that's based on global mean energy budget, you have forcing, energy imbalance, so the temperature or radiative response, and you can substitute any observed or model simulated historical period, so the temperature change, energy imbalance from heat uptake, historical forcing to this equation to have an estimate of radiative feedback, and therefore climate sensitivity. Oh, I forgot to mention, in this method, we use linear regression, assume this slope, which represents the strength of the feedbacks. But both methods are not truly equilibrium values. They're derived either using this linear regression or derived from transient historical states, assuming that your feedback that govern ECS should be constant over time. It doesn't change. Assume it doesn't change, so that you can use any transient estimate to infer true equilibrium or future climate change. This is a widely used assumption since maybe 2004, the first Gregory et al. Paper came out, but not necessarily true. So I will show use some comparison of different ECS estimates. So this one from observation, this is a PDF curve of likely range of ECS values based on this historical energy budget constraint using observations over recent decades. And you can see observed historical record give you an overall relatively low range of climate sensitivity centered around 2 degrees. So how about fully coupled models, those abrupt flow time CO2 simulations? So that's the blue bars. That's from SIMI 5 and SIMI 6 abrupt flow time CO2 simulations. And you can see models in general produce a higher range of climate sensitivity relative to observations. Also, I'd like to highlight two GISS models since I'm here in the building. Yeah, so I think this is ECS estimates from our GISS colleagues, SIMI 5 versions and 6 versions. Well, overall, the ECS estimate from GISS models are, sorry.
So the model simulations are using the same method, which is the historical, or are you
switch? Times CO2 simulation, I think, Gregory regression.
So you switch from one method to another. You switch from the budget to the.
Yes.
Is that a problem, or are you going to get to that maybe?
You steal my next point. I'm gonna say in a second. Yes, one is so this is from historical method, and this is from common model simulation. But before we assume both methods can give you same ECS estimate. Yeah, please.
Couldn't you do the historical calculation from the model simulation as well?
Yeah. Yes. Historical simulations.
I see.
Yeah, you have historical model simulated energy budget, surface temperature, and you can also estimate historical forcing from RFMIP simulation. I guess you're like in charge of the SIMI 6 RFMIP simulations.
Oh no, we contributed to.
Okay. Yeah.
No.
Yeah. Yeah. So the ECS, well, from abrupt flow time CO2, yeah, I should be clear. Abrupt flow time CO2 simulation from GISS model are well within the range of SIMI models, but compared to observation seems like a bit higher. So should we be worried about that? Does that mean that models have some biases? Actually, when this Otto et al. Using observations came out, it did trigger a lot of discussions and concerns regarding whether our models are too sensitive to forcing, so that this ECS, the blue bars, ECS are biased high. But yeah, I would argue that they're actually not looking at the same period. For observation, they're derived from historical record. And for the blue bars, although same ECS, climate sensitivity estimate, but they're derived from sort of idealized future scenario. So it's not a clean comparison. We want observation versus model over the same period. That comes our AMIP simulations. So these are, I believe I don't have to explain this, just the simulations run by atmospheric models, prescribed with observed SST and CS concentration. So now you can see if you use an GCM, give it released SSTs, then they can reproduce this low range of climate sensitivity. Even though their counterpart fully coupled models under above 4 times CO2 tend to produce higher values of climate sensitivity. So again, making an example of a GISS model, this is SIMI 6 version, I believe. This value from above 4 times CO2 from the Mark Zelenka's paper around 3 degrees. Well, I calculated AMIP simulation from also one of the DEX experiments, and using the historical energy budget, I got a ECS close to 2 degrees. So now you can see the difference. Well, these two estimates should come from exactly the same atmospheric components of the model. The only difference is SST boundary conditions. So for all AMIP simulations, the orange bars, they are prescribed with observed SST patterns. And for the blue bars, the fully coupled abrupt flow time CO2 simulations, the models generate their own long-term SST patterns, which feature this enhanced warming in the Eastern Pacific and the Southern Ocean, which almost look like the opposite to the recently observed pattern, which shows less warming or even cooling trends over the past 40-year period. So that.
But isn't there also a potential for state dependence too?
Yes. State dependence is like a global mean temperature dependence, feedback dependence on global mean temperatures. Except maybe over historical period, this temperature change is relatively small to about 4 times CO2. Yeah.
I'm sorry, but as far as what answer, it's like, can't you do take the couple models and have an apples and apples such that you're.
That's a great question. That's still like a 3 slides later, I will show the result. Yeah. You're basically leading my presentation.
I'm sorry.
Yeah. But thanks. Yeah. So let's do a hierarchy of a model comparison. So let's first focus on atmospheric model, which has this cloud parameterization, radiation scheme, atmospheric circulation, to see if those schemes are doing good job to reproduce this climate sensitivity. Turns out, at least for atmospheric components, they are this bias is not from the atmospheric component of the model. So that triggered or motivates people to think about this pattern effect. It basically means that in the community or in the literature for a long time, we have assumed that radiative feedback can be constant over time. But the pattern effect suggests it's not the case, because radiative feedbacks, which govern ECS, including cloud feedbacks, laboratory feedbacks, CS albedo feedbacks, water vapor feedbacks, all this feedback process may be sensitive to the spatial pattern of surface warming. So as SST patterns evolve, feedback may also change with time. So the implication of this pattern effect is that before we used to use estimates from transient state, transient simulation, transient historical state to infer ECS, because we cannot afford simulations running for thousands or several thousand years to get a true equilibrium. So we use transient states. But this suggests this transient estimate may be biased relative to the true equilibrium response. So that is oftentimes the estimates from transient states are called effective climate sensitivity, to be distinguished with the true equilibrium response. Yeah, to this point, any questions?
Yeah, but you know, if can
Sure, yeah.
but if you use the coupled model and if you use the transient run, so you can check if your historical gives you observed warming, then you can tell that your model is about right. So then you can use your historical coupled model to estimate this sensitivity.
Yes, that's exactly the slides I will present in a few minutes. And I don't want to upset you too early that fully coupled models have bias in simulating observed warming, so I just hold off for a few seconds. Yeah, but in a second, I'll show you exactly the result. But before we get to that, I just want to briefly mention the mechanism proposed for accounting for this pattern effect, why different patterns can give you different ECS, and why this observed pattern can tend to give you lower climate sensitivity. I won't spend much time on this. I think recent 5 to 10 years, a lot of the studies have been focused on this. Mostly we've gained insight from a large set of prescribed SST simulation to study how radiation feedbacks are sensitive to regional SST anomalies. This is so-called the Green function approach. But here I just want to briefly show a schematic from IPCC R6, which nicely shows this proposed mechanism linking tropical west-east SST gradient to tropical cloud feedback. The idea here is, like recently observed pattern feature, enhanced warming in the West Pacific and cooling in the Eastern Pacific. But warming in the West Pacific can usually be efficiently transported to the upper troposphere and warming entire lower troposphere due to the wake temperature gradient. So that over the Eastern Pacific, now you can see you have warming aloft, but surface cooling, so that this climatological inversion strength gets increased. And this environmental condition exactly favors more low clouds, favors low clouds to grow. And low clouds are type of clouds can give you like negative cloud feedback through the reflection of short wave radiation. But that's why this pattern is anomalous negative cloud feedback and therefore lower climate sensitivity. And this positive trend of the low cloud cover, lower tropospheric stability, and negative cloud feedback has been observed in EMI fronts and also in satellite observations. So pretty robust mechanism. So let's come back to, I should say this question because it was already proposed. Do fully coupled model simulations reproduce this low range of observed climate sensitivity or AMIP simulated sensitivity? So I actually, before I talk, I think Kate is here. Kate has done a nice work comparing this different ECS estimate for SIMI5 models. Here I focused on subset of the SIM6 models. The reason is that we want to accurately calculate historical feedback for each model, couple models, and also asked you in order to calculate historical energy budgets, you will need heat budget, heat imbalance, temperature change, which you can easily get from fully coupled historical simulations. But for this historical forcing, we call effective radiative forcing, is not usually available for each model. So you have to have a separate simulation with fixed ST to give you this data radiative forcing for each model, so-called effective radiative forcing. And now, thanks to SIMI6, so-called RFMIP, radiative forcing MIP project, which made a couple of the models available this estimate available. So we use all of these models that have historical forcing, which currently have 8 models, including this model I'm highlighting here. Yeah, again, I'm showing first the blue bars are from emipyrons, pretty low, centered around 2 degrees, including this model. And second, this is historical simulations. You can see over same period now, and same atmospheric model. It's just a different SSTs. One prescribed, one lab model fully involved. Fully coupled model usually give you much higher climate sensitivity. While in the case of the GISS model, it increases a little bit, but for other models like HAGM, 10ESM, it gives you much higher climate sensitivity. And those estimates are as high as their above 4 times CO2 estimate. But in a second, earlier I said there should be a difference between historical and the future, right? Accounting for the evolution of the SSTs. But this means that fully coupled models usually can't accurately simulate this historical pattern effect, which likely means their patterns are biased, something wrong with their pattern. So I looked at those 8 models and we further expanded to 16 large ensemble, semi-5 and semi-6 models, large ensembles account for natural variability to carefully examine model with observation in terms of a SST trend pattern over the recent 42 years. So this is just a recently published paper led by Rob Wills, now at NCAR. Yeah, you can see models. We analyzed over 600 ensemble members, and none of the ensemble members can simulate observed cooling trend in the Eastern Pacific and the Southern Ocean at the same time. So in general, models have biases in the Eastern Pacific and Southern Ocean, where observations show cooling and model says, no, I want you to warm, right? And this is a observation versus multi-model mean. Here I'm showing the difference between observation and GISS model again for semi-6 version. You can see still, yeah, consistent with the other semi models, most pronounced biases in the Pacific sector. Eastern Pacific cooling and West Pacific warming are not accurately represented.
So the GISS model doesn't stand out as being particularly weird because it should be, because this version of the GISS model doesn't have stratocumulus decks.
It did in CMF5. It very much stood out as weird for exactly the reason that UA is explaining.
Yeah, and this SST pattern, I think, is biases is pretty common across semi-6 models, I think. Yeah. Do you think if I exit and show another slide, it will be weird screen? I can skip, yeah. Are you sure? Or I can.
I'm not sure, but you can try it.
No, yeah, I just have another slide, which is hidden now, to evaluate like each individual index, like what is the gradient or some means on the ocean, each ensemble members. Usually, well, over 600 ensemble members, only quite like 1 or 2 ensemble member can simulate this kind of a gradient or tropical southern ocean gradient. And GISS model is one of the models that like also have this strong bias. Like none of the ensemble members can simulate what's the gradient or southern ocean cooling. So regarding this model observation mismatch, a lot of theories have been put forward to explain the differences. The prevailing idea is always natural variability because this cooling pattern looks like just negative phase of a PDO or IPO, or some people argue for Atlantic Ocean here eventually influenced tropical Pacific through atmospheric teleconnection. So that's one school of thought. Some other people also argue for biases in force response or forcing itself, like related to aerosol forcing, volcanic forcing, or CO2 forcing, like our Richard Seeger and Lamont, who argues that this trend, this cooling, Eastern Pacific cooling should be just a transient CO2 force response due to ocean thermostat mechanism. And this process is misrepresented in current models because of their mean state biases. So that's another idea. Yeah, so among these different ideas actually could lead us to different projections of future pattern and ECS. If this natural variability, then probably in the coming decades or centuries, we might expect this pattern to reverse. So probably this model projected near future warming pattern is still fine. So we should expect a higher climate sensitivity. But if this cooling pattern is force response, and in the coming decade, like CO2 force response, in the coming decades, as long as we have continuous CO2 forcing, then this pattern could persist for couple of decades or centuries. And in that case, we may have a lower climate sensitivity in the coming decade. So understanding this causes is important for ECS and transient warming constraints. But that motivates me to understand what causes this observed pattern and why models can't simulate that for my postdoc.
I'm sorry. So I can definitely understand that it's an important bias and it's probably involved, but if you actually did some simple correlation, right, of this SST bias, whatever measure you want to use with this ECS, you're saying that that's very strong. Like you actually made a figure, right? Because you're implicating this failure to reproduce the historical SST trends as basically the primary driver of this kind of disconnect in ECS. If you actually made that plot, you're saying that it would be a strong correlation.
Which correlation are showing?
So it's the before you were showing the disconnect between the coupled models, historical simulated ECS, and that from the AMIPS.
Oh, you mean the historical estimate versus abrupt flow amplitude.
Yeah, right. So if part of that is related to this failure to reproduce this historical SST trend, right? I mean, I'm just saying if you did a correlation of those two, you're saying it's a strong relationship. Maybe you have that figure or something. Yeah.
I don't have that handy except to that.
But maybe that's
yeah, like something like this.
I mean,
Sure.
I actually don't think you necessarily need a correlation because you've got a really strong physical argument, kind of from first principles, that a lot of the low cloud feedback is driven by what's going on in the equatorial Pacific. And specifically, if you've got a really strong gradient between the eastern and western Pacific, you're going to be able to, really increase the warming of the troposphere and set up a really strong inversion strength feedback, where that's going to make low clouds. Whereas if you don't have that, you don't get that. And so, I think there's just a really strong kind of first principles physical argument for if you mess up the observed warming pattern in the equatorial Pacific, you are going to mess up your climate sensitivity. Is that?
Yeah, that's so. The correlation you said is like between AMIP and full couple models.
Yeah, I mean, I guess it's also to Andy's point. Andy's saying that there are physical reasons in our model that why we may not be able to reproduce some of these SST trends. And yet the GISS model also interestingly showed less of a disconnect in terms of the ECS. If you go back to that, there was the histogram that you showed before.
Yeah. That could actually be because we don't have those clouds operating properly. I think it's a great question. And I guess another way to say that is maybe there's a combination of things, how that feedback is operating in the model and how its SST is.
Yeah,
that's what it must be. It must be if you didn't look at let's say SST trend, but how that's seen via the feedbacks, right? If you did that, then that may be through that. Yeah.
It'll be fun to see what E3 looks like on this plot, right?
Yeah.
Where we have stratocumulus.
Yeah. So I understand the point is what causes this pattern could be something like driven by low clouds. So low clouds also can cool this coupling problem. But I also it could be, so this pattern itself is driven by atmospheric forcing from clouds. So you miss clouds, you also miss this cooling. There's a couple of problems. But at the same time, I want to point out this is like a 40-year trend, cooling trend. So we tend to probably the ocean also play a bigger role, like setting this low frequency variability. I don't know, like what can cause 40-year trends in cloud feedback that can strongly force the ocean surface temperature to give you this cooling trend on low frequency variability. Oh, it's not necessarily variability of the trend. Yeah.
And maybe you're going to get to this. I thought there was also the idea that freshwater influx from Antarctica was possibly implicated.
Oh my God, that's the second whole part of my presentation.
I'm sorry.
But I believe I wrote that in my abstract, so I'm still leading.
Okay, well, I'm sorry, I didn't read your abstract, but I just saw your bullet points and it wasn't mentioned in your bullets.
Yeah. I didn't list it here because I wanted to say, I'm thinking of.
Okay.
Yeah. So among this proposed method, indeed, another obvious model bias is a lack of a freshwater input. So basically, current generation models are unable to simulate imbalance of freshwater input, meltwater, so from Antarctic ice sheets melting. So let's and this idea actually, lack of a freshwater, can they explain some of the model observation discrepancy in the Southern Ocean? This idea has long been considered in the polar community. So, for example, I'm showing this Crick's paper. I hope he's not here, right? Yeah, I was excited to talk to him. So this is I believe that he impose an abrupt freshwater forcing to GISS model and run an ensemble and find in response to this freshwater impulse, you have SUS. So this is a zonal mean southern ocean temperature response, surface cooling, subsurface warming, and surface freshening, well in line with observations. So this idea has been proposed. Well, the actual freshwater input might explain some of the observed Southern Ocean changes, and the lack of a realistic freshwater representation in models could explain some of the model observation discrepancies. But most of the attention in this polar community or freshwater community has been focused on Southern Ocean local response. If you look at their paper, mostly just polar projections or this cut into 20 degrees without extending to the whole globe. But I was more interested in global impact, like global SST pattern or climate sensitivity. A few models actually did look at the global mean surface temperatures, and they argue, well, in the near future, 21st century, for example, this GFDL model, when they account for this continued freshwater forcing, you would expect delayed global warming. And the reason why meltwater can reduce global mean temperature is proposed to mostly arise from more efficient ocean heat uptake, because you change your Southern Ocean vertical temperature distribution, you have more heat stored in the deep ocean, makes your Southern Ocean more efficient, heat uptake more efficient. That's a key idea. But I was interested in, well, if you think back, looking back this global energy budget, in response to external forcing, greenhouse gases or whatever transient forcing, the way the Earth tried to balance this forcing and keep the temperature, immediate temperature through not only heat uptake on transient time scales, but also radiative response at top of the atmosphere. So you have heat emitted at the top of the atmosphere governed by radiative feedbacks, lambda term. And you also lose heat into the deep ocean governed by heat uptake efficiency. So eventually this global temperature trend on transient time scales should be determined by both terms. One, lambda the kappa, so radiative feedback and heat uptake efficiency. One represents the efficiency with which heat is emitted at the top of the atmosphere, so upward direction. And one represents the efficiency with which heat is stored in the deep ocean, two directions. But so far, most of the attention has been given to this direction in response to Antarctic meltwater, because you add something to the deep ocean. And this part, lambda change or feedback change, climate sensitivity influence has received less attention. So we wanted to ask, does Antarctic meltwater primarily influence the warming rate through changes in heat uptake efficiency or feedbacks or both? Which one is important, more important in changing the global temperatures? Most of my PhD work has been using CESM, so I'm presenting results from two CES1 Chem 5 simulations, the so-called Hosing rounds. A little bit different to Craig's abrupt forcing rounds. These are transient with all realistic historical forcing and 21st century RCP rated forcing. One looks at recent decades, 40 years, 33 actually, and one looks into 21st century. And I believe the first author, also co-author on my paper, is Shanna. I said I'd probably give a sea level rise seminar that Craig used to organize at some point. Yeah, so for this huge ensemble, the imposed meltwater is estimated separately by an offline ice sheet model, so I consider more realistically in response to forcing. But for historical one, because observation also very uncertain, so they eventually impose a rather idealized amount of fresh water, which is 2,000 gigaton per year from interior ice shelves, which is way higher than observational constraint. And also, I think 10 times higher than what Craig used to force the GISS model as abrupt forcing scenario. So first, I looked at their local response to make sure that this model is doing reasonable thing relative to other models. So this is Southern Ocean zonal mean temperature response and contours as salinity over trend over historical period, 21st century, in their control run without meltwater runs and the difference. So this difference shows the response to meltwater. And you can see cooling, so blue, red, and dashed contours mean cooling at surface, warming at depth, and the freshening trend at the surface, which is largely consistent with other Hosing rounds, including GISS models simulations. And more importantly, if you compare with observations, I would say, well, meltwater runoffs here obviously still underestimate observed trend, but a qualitatively bring the model a little bit closer to observation by producing this net cooling trend and surface freshening, which is not seen in the normal historical simulations. So this is only me idea if you focus on the Southern Ocean. But yeah, as I said, I'm interested in global SST patterns. So here you can see global SST trends. That difference shows you the response. The Southern Ocean, Antarctic meltwater induced Southern Ocean cooling extend to the low latitude, mostly in the Eastern Pacific, forming this La Nina-like cooling pattern. And you can see here is apparently closer to observation, not as strong as observed cooling. But if it brings the model closer to observation by producing this net cooling trend, which is usually not seen in any of the similar historical ensembles. So next, next we see this global mean temperatures, and consistent with other models like GFDL models. CS1 here, when adding anomalous fresh water can also reduce global mean temperatures by 20% over historical period and by 28% in the future, which means in the future projection, accounting for actual meltwater can delay the projection or reduce the warming projections. Oh yeah, and I also want to mention that a lot of CIMI5 or CIMI6 models tend to overestimate recent historical warming. It's known as a common bias in GCMs. Some people argue it's because of bias in aerosol forcing or something, but we actually found this is observed warming trend over this period, over a historical period in observations. And adding meltwater can actually reduce that model biases or produce something similar to observation. So could be like this lack of meltwater can also explain global mean temperature biases over historical periods. Yes.
What would you say is the leading, or how big is the uncertainty in the SST map in general? Is that a factor from, is that, I don't know where those records come from. It's easy to imagine satellite records. There's going to be a lot of trouble with cloud contamination. Clouds are very regionally,
I mean, uncertainty observed as it observations?
Yes, exactly.
Yes.
Is that something one can just neglect, or is that something that could be playing a role?
It does have some uncertainties, but it's much smaller than uncertainty or the mismatch between observation and the model biases.
Okay.
Yeah, there was a paper like a comparison of the independent SST data, and then they match up perfectly. Almost,
really?
yeah.
Okay, good. With the pattern.
With the pattern, yeah, and the global time series is also kind of matching up perfectly,
Okay.
even though they're completely different from coming from a different data set.
I'm interested to see that. Okay, thanks.
Yeah, that's a good point. Yeah, so this global warming trend. So
So sorry.
yes.
I'm a little confused by the implication of you include the meltwater flux, and that makes the high sensitivity models kind of notorious, too warm post aerosol era. That makes that look more like observations. So you're basically saying that the high sensitivity models are credible, but there's no such thing as equilibrium, because you have this constant influx of meltwater, and therefore the models are accurate. So you double 4 times CO2, and what they do with respect to cloud feedbacks, that is accurate, but they do not take into account this meltwater flux.
Yeah, I think it was referring to a recent thinking of emergent constraint. They found a lot of studies found, their recent similar historical warming is correlated with this equilibrium constant ECS. So models that tend to overestimate historical warming might be biased because they have this too strong biased response to CO2 or biased response to aerosol. So they infer if models tend to overestimate historical warming, they also tend to overestimate ECS. So their biased, their response to CO2 is biased. But here, I think that's exactly the point. By looking at these freshwater simulations, we show that even models have high ECS, But on at transient timescales without meltwater, they tend to overestimate observation. But adding this meltwater can bring the model over historical period closer to observation without changing their equilibrium climate sensitivity. So that's still possible. So if in nature this low observed warming is at least partially driven by meltwater, which is not included in models, then it could be the reason why models tend to overestimate. And that implies that those high ECS values may be still possible. You can, at least you cannot use this correlation between recent and future to rule out those high climate sensitivity. Does that make sense?
It does, yeah. I'm thinking about the implications for trying to use the paleo evidence to constrain ECS, but we can talk about that later.
Yeah. Yeah, I think this, like the reasons that like meltwater, some wind nudging rounds, which correct for Southern Ocean, we ended up finding low climate sensitivity due to this pattern effect without changing their any long-term warming. So, which can be used to like apply against those high emerging constraints. If we don't have a clear understanding of how recent or transient warming is connected to the future warming, then simply using emerging constraint might be a little dangerous to just to rule out high or low climate sensitivities.
But you said yourself there's a caveat that they used, what was it, 10 times?
Yeah.
Yeah. So how did they explain that?
Yeah, so actually, let me show this again. So the fact that we're overestimating or we use a lot more fresh water to force this model, and this actually the model simulates freshening, surface freshening is still weaker than observation. So from the model perspective, this model is probably not sensitive enough to freshwater input. And actually in the polar community, they found the amount of fresh water needed to cause significant change in models is very model dependent. Like CES1 needs a lot more fresh water. And in some like Canadian model, earlier version, they need only a fewer amount that can do the work. So this is first is model dependent, and second, well, if you think about this remote effect, like remote tropical SSTs or remote tropical feedbacks, as a response to surface freshening trend, observed freshening trend, and our models still underestimate that surface freshening. So maybe anything we got about feedback response is still underestimated in this model compared to observation. Does that make sense? Yeah, so the only last part is to quantify what terms, so heat uptake and feedback, which one explains most part of the global warming change. For heat uptake efficiency, we found it's strengthened, which is not surprising given this change in the depth of the Southern Ocean heat storage. More heat is being stored at depth. But for feedbacks, we also found it's strengthened. It becomes more stabilizing, which gives you lower effective climate sensitivity. Not exactly as the low climate sensitivity degree.
Is this not on? Oh, God. Okay.
About in this hour in a second. Yeah.
Yeah.
It's working. Yeah, so we're seeing lower effective climate sensitivity, a little bit closer to what AMIP rounds would give you, about 2 degrees. And we argue this is due to the pattern effects because you see this cooling. First, the Southern Ocean local cooling, and then this cooling extend to subtropics. So in the subtropics or tropics, this strengthened west-east gradient can give you, as mentioned again, this lower tropospheric stability and inversion, which gives you more marine stratocumulus clouds. And in the Southern Ocean, in this ocean force surface cooling can reduce air sea temperature gradient, can give you more stable boundary layer, which gives you more high coverage stratiform clouds. And both types of low clouds are we observed this possible trend in simulations, which can give you more reflection of a short-wave radiation. So that's essentially a strong negative cloud feedback process that can stabilize the climate system and leads to lower climate sensitivity. So the very last question is, what are the relative roles? Which one plays bigger role here? So we come back to this equation, simple energy budget. This is approximation to the global warming rate. So here we're just simply substituting forcing, feedback, and heat uptake efficiency, 3 terms. And just using these 3 terms, we find this can pretty accurately reproduce the actual warming rate out of the simulations. So now we're confident in this approximation. We can just play with it using different terms to get the individual contribution. For example, we only let feedback change, or we only let kappa change, and keep the other unchanged. So we can have an estimate of how much of the warming rate change is coming from feedback change or heat uptake changes alone. So this is just a simple linear separation. And we found feedback and ocean heat uptake efficiency each account for approximately 50% of the total change in global warming rate in both ensembles. So the implication of this is that so far for this freshwater idea, although people think maybe it changed the Southern Ocean or they give you more Southern Ocean cooling, Southern subsurface warming and freshening, and this can have a big impact on global warming because your Southern Ocean now can take more heat. But we show that actually changes in feedbacks that is due to the pattern effect also have a substantial impact. It can account for up to 50% of the total change in global warming rate. It's not only just the heat uptake change. At the same time, you also lose heat at the top of the atmosphere. So the implication of this result is when we think about this recent observed pattern, well, first we found this meltwater can have both local and remote changes, bring the model closer to observation. So when you think about this observation, we still cannot exclude the possibility that natural variability is part of the reason. But looking at this meltwater simulations, they probably suggest that this observed pattern maybe at least partially is a forced response and forced by meltwater forcing. And if that's the case in nature and in other models, this forced response may persist in the coming decades, different to what models usually project.
Well, can I ask about, so if you look at CSMLE, are there any members that show this pattern?
No, at least not tropical cooling and Southern Ocean at the same time. Yes.
Do you think there could be a role for uncertainty in the other factors you listed as well as contributors? For instance, it feels like, there's uncertainty certainly in volcanic forcing historically. So if all CMIP simulations are adopting the same scenario, is it possible that, another scenario could contribute to improved SSTs?
I do think other factors like volcanic forcing, aerosol forcing, and also social forcing could play a role here. This is just another proposed possibility of a forced response against natural variability, which suggests there's another possibility that we may expect this pattern to persist in coming decades. So ideally, we would want to test this results in other models like GISS models to see if this is robust across models.
How about like ocean parameterizations, like mesoscale eddies or those kind of things, which might enhance the mixing, so which can enhance or which can increase kappa or something in your.
Oh, for this result?
Yeah.
Oh, yeah, that's a great point. So I do think the quantitative results, like we found kappa and lambda each account for 50%. This kind of number should be very model dependent. And this result, we eventually see teleconnection, to see tropical feedback changes. All of this process could be model dependent. For example, how models simulate Southern Ocean, like mean state, or Southern Ocean temperature response to freshwater input.
Yeah.
How models represent teleconnection. How models simulate tropical cloud feedback due to different cloud parameterizations. All of these factors could give you intermodal spread. So quantitatively, we would like to see this tested in other models. And I would expect some model dependency as well.
And the ocean overturning is also.
Yes, like kappa, the heat uptake change. I do think how models simulate Southern Ocean convection.
That is
their mean states. Yes, that could largely change our results about kappa. Some models have a deep convection, some doesn't, some don't. So that could give you probably different heat uptake efficiency.
So implications we cannot constrain the ECS in the future. We still have this range 1.5 to 4.5 or 2.5 to 5.5. This range not gonna shrink.
Well, I'm saying that for this freshwater input, freshwater result, that could be very model dependent. For without water, just a semi, we see that's like it. Well, currently semi-5 and semi models are very different, diverse parameterization, right? But still, none of the model can simulate the observed cooling. That's big problem. So yeah, I don't have a clear answer like what you said should be, like a narrow range or more higher range. Yeah, but qualitatively, maybe this is the indicative of a transiently lower climate sensitivity in the coming decades. Yes.
Sorry if you talked about this already, but you said that it was really the meltwater causing this pattern effect, and it was really having an impact via the feedbacks. Do you have any sense for the partition between it's this Eastern Pacific teleconnection, and it's the fact that you're able to maintain this really strong gradient between the Eastern and Western Pacific, and so it's really the inversion strength putting a lid on it and making a lot of clouds over the Eastern Pacific, versus the Southern Ocean is not warming up as much as we think it should, and therefore we're not getting the SST component of feedbacks in the Southern Ocean. So basically, like, is it Eastern Pacific story, Southern Ocean story, or both?
That's a great point, and I haven't quantified that. It's just qualitatively we see that increase in both regions, but I don't have a clear answer as to which region is more important. And I guess this could be also dependent on the magnitude of the SST cooling. For example, in historical, this is the cooling SST response, and we note the different color bars. In the future ensemble, because we impose a lot more fresh water, so induce a lot more cooling, which give you stronger tropical response. And while in the historical, probably less significant cooling response. That's why when you look at low cloud response, you see much stronger subtropical response in the future ensemble with more cooling and freshwater input. But in the historical, probably only Southern Ocean. So that's probably also surface SST magnitude dependent. So and I guess that could also be model dependent, the quantitative answer.
Does it mean like local circulation is enhanced in a simulation?
I closely look at SST. I believe so.
Yeah.
Yeah.
Yeah, because like there is a discrepancy in the models, like that in the future, like local circulation should be enhanced or weakened, and then there is some kind of like discrepancy in our argument, the scientist argument. So
yeah, now that's also tied to the surface SST gradient.
Yeah, right, yeah.
It's a couple of problems.
Yeah.
Just going to interject with one comment from the chat. So David Rind had a comment, and he said there is a subsequent Rye et al. Paper which may be submitted. He's not sure of the status, but it did look at the global response to southern hemisphere meltwater input. And he says the reduced tropical warming in association with greater greenhouse gases was influenced by reduced water vapor, which was initiated by high latitude cooling, but which by reduced global warming is affecting water vapor everywhere. So
okay, yeah, I guess he's arguing that we're here mostly focused on low cloud feedback, and he's arguing what bigger feedback plays a bigger role in GISS model. Could be
Yeah, and a model that lacks stratocumulus decks.
yeah.
So is it possible, like in the kind of like traditional studies, like we can decompose a lot of climate sensitivity into the like different contribution, right? Like low clouds, water vapor, etc. And now you add another degrees of freedom, like kappa lambda kind of like thing, or the pattern effect ish. So like
yeah, I guess for feedback response we can certainly separate, like using kernels or something separate to look at contribution from low clouds, lab-saturated water vapor, CS albedo feedback. But the heat uptake efficiency, I should point out, it's more on transient time scales. So
that's right,
transient time scales, so you have heat uptake. But on equilibrium time scales, there's
I see. Right.
Yes.
So is there I assume that people have known about this SST bias for quite a long time, people working on ocean models. And has it been something that hasn't seemed important, or have they been working on that? Or do you think that that's an important goal then now for it, for us to trust future scenarios that we have models that can reproduce the basic features of SST trends?
Yeah, I guess this is really getting a lot of attention recently due to this pattern effect and an implication for future climate change. For a long time, I think the most prevailing idea is still natural variability. You see this also due to the limited coverage of observation, like recent 30 years, that's probably just a negative phase of a PDO. So in coming decades, we just expect it to reverse. And also some people think we may not have enough sampling of the natural variability. Yeah, and the reason, well, I guess like the first figure I'm showing, like from Rob Wills, we're trying to argue that if you look at large enough, like in MPL grand ensemble, 100 members, and CES2 also 100 members, and none of the member can simulate this cooling, probably mean that our models are biased in some force response. Because even in like a tropical convective region, tropical West Pacific, where there should be like less natural low frequency variability, but still models don't reproduce that enhanced warming. So probably just some like a forced response that is misrepresented in models. I think this is more like I wouldn't say it's a recent idea, but it gets a lot of attention on this forced part recently. Katie, you want to say something?
I'll save it for later. I don't want to go off on a tangent about the oscillation maximum.
Okay. Yeah, and yeah, I should mention, yeah, there are also like a constraint from Pato perspective. Yeah. So I can finish my second implication, which is, yeah, I guess we've already covered. So to understand the impacts of meltwater on global mean temperature, but I guess this is tested in GISS model too. You would not only need, not only southern local response, but the remote tropical response, either through cloud changes or water vapor changes. So to accurately project future climate change, you will need the better representation of meltwater and its impact on both local and remote climate. So which means not only you improve ocean parameterization or whatever components, ocean components, but also you have to consider this teleconnection through either atmosphere or ocean and also tropical cloud feedback or water vapor feedbacks. Yeah, this is basically the end of my talk. So I just started with this pattern effect, showing this discrepancy between historical and the future, which can explain a part of this ECS estimate. And then if we trust the model, if models are reliable, we can trust their future projection, which means nature could evolve in the future like that. And then we should expect higher climate sensitivity, 100 years or in the true equilibrium. But models are not perfect. They have this significant bias over historical period. Now the ensemble member can simulate historical period, historical SD pattern. If it's natural variability, then that's probably fine. But if it's forced response, for example, due to the lack of freshwater forcing, then we might expect this pattern to persist for coming decades, and that give you different ECS. But still, yeah, like Anne pointed out, could be other factors. Volcanic forcing, aerosol forcing, we still don't know. So the better understanding of this problem and better constraint or projected on the future warming patterns is important for, I should say, ECS and also transient warming constraint. Yeah, I think I've managed to cover all of my slides. Yeah, in 15 minutes. Yeah, thanks. Thanks.
Well, thanks so much. Do we have any more questions or people in the chat? If you want to raise your hand, you can and ask it or enter question in the chat. Or anybody else here?
Is there any model, like current general model GCMs, which has like interactive freshwater parameterizations? Like, so like, you mean like most of the model, like we have to prescribe the freshwater input, right?
I wish Gavin could be here. I think that's a motivation why GISS model wants to build more interactive. I think current generation of the models don't simulate any imbalance of freshwater from a continent. They only have a runoff from like snow or ice accumulation.
Oh, okay.
They don't have freshwater imbalance at all.
Okay.
So we only have this kind of a hosing runs, which you artificially add anomalous freshwater input to the model.
Mm-hmm.
I had one question. This is more just reflecting my naivete about the issue, but in terms of the communication from the southern hemisphere high latitudes to the tropics, so Okay, so David proposed, maybe there's a role for the water vapor feedback and things like that, but have people talked about a dynamical component to that? So like the latitude of the jet, yeah, so that component of that pathway, because models, do they have their biases in the jets may contribute to that? Has anyone tried to explicitly look at that part of it?
For the mechanism, the teleconnection itself, actually a lot of the recent studies trying to propose the atmospheric pathway. For example, this zonal mean heat transport, you would expect when you have a cooler southern hemisphere, you would expect acidity to shift towards the northern hemisphere, which change the water circulation. So that's atmospheric pathway. Also could be due through oceanic pathway, like tropical, subtropical cells, which carry the vect is surface temperature anomalies to the tropical upwelling regions. And also some recent work, including my work, look at usually the strongest teleconnection happens in the eastern side of the Pacific, this eastern Pacific and the southeast Pacific sector, where climatological winds here near the Andes can most efficiently affect surface temperature anomalies into the tropics. So there are quite a lot of evidence pointing that this high latitude surface forcing can influence low latitude climate.
Right, any more questions?
But lower two panel, left panel, the time span is all 40 years.
Yes. Yeah, they're over the same period.
So my question is that for historical round, they're more than 160 years. Have you ever checked? You carve up many 40 years period. So have we checked every 40 years? Are there some 40 years have some pattern similar to observation?
I didn't check that rounding 40 years, but we look at the long, like from 1850 to present day, for example, over 150 years trend.
No, I mean, because if you have, for example, there is in ocean, for example, there is 50 years oscillation.
Oh, and
If you put this window in different place, then pattern could be different.
I think I don't have a specific papers on the top of my head, but I think this recent period starting from 1979, it shows the strongest this cooling pattern, and models where the biggest model biases happen is recent. Now also because I think a lot more uncertainties in observations prior to 1979, the satellite era. So usually before 1979, we don't have like a clear model observation. They usually just a long-term trend without looking at each individual chunks.
For example, yesterday, Larissa showed some century period oscillation, right? That could happen in that area, right? Mm-hmm. So if there's a century of oscillation, so if the sample in different time span could make difference, right?
Yeah.
Because ocean period is much longer than atmosphere. Could it be 20 years, 50 years, 100, maybe 1,000 years? The time period really matters. You cannot use this 40 years to judge this internal variability.
Yeah, but look, the thing is that, when you start this historical experiment, you started with some, control, right? And when you start this historical experiment, it's possible that, a coupled model drifted away from the observed state already.
I'm talking about the vacillation.
But I'm confused. So the observation here is just the satellite period, and the historical is from 1850.
Yes.
We're comparing 150 to 40 years.
No, 40 to 40.
40 to 40.
Oh, okay. Everything's just a satellite.
Yeah.
I missed that entirely.
See, if you compare 100 to 100, like it's 1850 to present, the models actually produce well consistent with observations, because observed trend over the last 100 years is pretty uniform. It doesn't show this very spatial heterogeneous paper.
Okay, you check the
pattern.
Lot of 40 years is consistent with 160 years, right?
I mean, the longer period give you like more uniform pattern, which is captured by models.
You took a long PI control, saying thousands of years and subsampled that for trends and plot a PDF of those trends, you still wouldn't probably see something like this as a claim, right?
Yeah. Yes.
If I remember correctly, like previous version of the GFDL model produced something like La Nina kind of patterns of the SST warming, right?
It's like spatial.
Yeah, that's like
Yeah.
you have the overlap.
I think that's a look at 1% CO2. So like a transient warming, and also he subtracted the tropical mean to show you this relative pattern. So it does like show Eastern Pacific warming less, but it's not actual cooling trend.
I see.
So there are some ideas about like future should look like La Nina based on ENSO. Like if models better simulate ENSO diversity, and those models tend to like GFDL 2M tend to give you like a more La Nina like transient response. So that's also one of the ideas.
What fraction of the CMF6 models get an enhanced east-west gradient on your full-time creation?
Clara, I want to try this.
Yeah,
and
we'll do
give
it now.
you-
We're at the end anyway.
I had to,
Escaped out.
yeah. Let me show you this. This is an probably don't have to show full screen. So this is a nice study in Rob's paper where we quantify this west-east gradient, for example, and this observation, 3 observations, a little bit different but pretty consistent, shows a positive, which means strengthened west-east gradient, and this 16 models with their each individual ensemble members. You can see only probably like a 3 or 4 ensemble out of the 600 ensemble members could produce a positive trend in west-east tropical Pacific, and this is in the mid-southern ocean. So nearly the majority, like I would say, nearly 600 members failed to produce this.
What about once the climate has warmed to more, and certain hypothesized physical feedbacks can come into play?
Would it be like high ESM models?
No, there are some hypotheses why in the climate this gradient should increase for some period of time. Evaporation feedbacks and things like that.
Yeah.
I'm not remembering the details very clearly, so I apologize. My question didn't make sense.
I think there are some theory basis, like from earlier Manabe's papers suggesting that under CO214, you should expect a weakening of the water circulation due to the evaporation, the climatological cold time.
I'm remembering the opposite hypothesis by some people at the model.
Yeah, Richard Seeger.
Yeah, maybe Richard. Yeah.
Yeah. Because so I guess the discrepancy here is the time scales. On equilibrium time scale, probably we should eventually see this enhanced warming in the Eastern Pacific. But on transient time scale, there are so many things that could change this, like ocean thermostats, this upwelling. I think even Richard is arguing this transient cooling response. But on long time, like true equilibrium scales, I think he still thinks that should be like so whether we're experiencing some transient force response, which is random natural variability, or we already see some equilibrium response, I think we don't know yet.
What is model O, and why does it do that?
That's my question to all the model experts here.
But what is model O? Which it's a particular model, right? These are
like this
You're
model,
not-
like this GISS model.
yeah, but there's one that got the answer right. I'm just curious, what is that model O that's
I
labeled
think
O?
point is, for example, the old model can produce tropical, but then it misses the southern ocean. So now the model can simulate both regions. Well, if we focus on cooling these regions at the same time, so it happens to get this tropical cooling, and then it misses the southern ocean.
Where does the so like Fugler at Princeton has looked at the upper tropospheric temperature trends? Where does that kind of camp of literature fall with respect to this? Is that consistent with this claim of a lack of a representation of SST trends? Is that simply a reflection of that, or is that somewhat separate? Sorry, I'm not putting you on the spot, but just curious if you've read those papers. Yeah.
Well, he's like recently, 2019 or 23.
It's like called Fugler.
Yes, I think he focused on observation, like set of observation, and in upper troposphere, the temperature stability and tropical temperature, like he used the metric of warmest SSTs relative to tropical mean, and still find I think a similar mechanism. Eventually, this recent anomalous negative cloud feedbacks is due to spatial pattern where warmest region have warmed more. The warmest regions here I define as West Pacific, and he used more like a histogram or beam analysis. But I think the idea is this warmest region have more, which can give you lower tropospheric stability, the strength.
Were you at the Isaac Held talk at the APAM?
Yes.
How do you think about it? Like
for ozone?
Yeah. So the idea is that ozone, the decrease might affect this kind of SST pattern.
This is in the tropics. Right?
That's a brilliant idea. I actually yesterday I asked my current postdoc Lorenzo if I should show some results from this project. So I'm also working with Lorenzo to think about this. Some of my PhD work look at this how winds influence the tropical spatial connection, and that motivates me to think if the recent observed jet trend is caused by ozone depletion, and whether ozone depletion causes any tropical ST patterns. So we run CES1 against CES1 single forcing experiment. We do see strong tropical cooling in response to ozone depletion. Yeah, but through a surface pathway, through SAM and then trade winds.
So not via the TTL, which is what he was saying.
Yeah.
Which is a little
not. But we haven't clearly examined the upper tropospheric pathway. We're focused on the surface pathway. And actually, Dennis Hussman in University of Washington, he already published a paper on this hypothesis how SAM, this ozone depletion, could remotely influence tropical STs in observations, but more like the theoretical hypothesis.
Is that a recent paper? Or kind of...
Yeah, very recent PNAS article. PNAS commentary paper. Yeah.
Okay.
Great. Well, thank you so much.
Yeah.
And thanks everyone here. I think it's been really great. So I think I'm going to wrap it up. It's about 12 minutes past, but stay tuned for the next one.
Yeah. Thanks for coming.
And thanks everyone for attending virtually. So there is a recording too available for people who aren't able to make it. Thank you.
Nice to meet you. I'm Bruni, and then I'm sometimes still in your office at Lamont because I